Well, let's take a look at Chapter 4. Our first section is inverse functions, and it talks about one-to-one functions. So let's talk about how to identify those. Now, one-to-one function says for every x, there is only one y, and for every y, there is only one x. Now, that's a hard definition to work with, so we got an easier definition of a one-to-one function. And it says if you have one of the following, it is not a function. So if you have a even power, it's not a function, or one-to-one function. It's not a one-to-one function. There we go. If you got the absolute value. If you got the plus or minus. Simple. Then it's not a one-to-one function. Now there are some other items that also fit into this list, but those are the main ones you see in algebra. Unless there is a condition put on x. For example, y is equal to x squared. The fact that it's got an even power means it would not be a one-to-one function. But if we put a condition on there where we say x is greater than 0, they're usually putting that condition on there to make it one-to-one. And we'll see some, or talk about some examples in the video where that doesn't apply. Now we have a vertical line test that determines if something's a function or not. Just to refresh your memory on that, it says if any vertical line intersects the graph at two or more places, it is not a function. Now we also got a horizontal line test. It says if any horizontal line intersects the graph at two or more places, it is not one-to-one. Excuse me. It might still be a function, but it's not one-to-one. So the horizontal line test just checks the one-to-one portion. Okay, so our first topic here, identify one-to-one functions. Well, if I have this right here, y is equal to x squared. And it's a question whether it's a one-to-one function. The answer here would be no. It's got even power. So that's not a one-to-one function. If you got y is equal to x to the third minus 1. The answer here would be yes. This is a one-to-one function. So we got x squared plus y squared is equal to 4. The fact that this has an even power means no, it's not a one-to-one function. Now if we looked at the graphs, first off, this one right here would not be a function because it fails the vertical line test. So if it's not a function, it's definitely not a one-to-one function. If we look at this graph right here, well, I can draw a horizontal line here that intersects at two or more places, which means it's not one-to-one. So by consequence, it's not a one-to-one function. But if I had this graph right here, if I draw a horizontal line, it intersects one place. Draw another one place, draw another one place. No matter where I draw a horizontal line, the most it'll intersect is one place. So graph-wise, that would be a one-to-one function. Grab a drink. Let's clear that off. Now they say determine whether two functions are inverses. So let's first get to the point where we're talking about inverses. Reason why we look at the one-to-one part. If a function is one-to-one, then it has an inverse. If a function is not one-to-one, then there is no inverse. Now algebraically, let's talk about what inverses are. So inverse functions. F and G are inverses, or are functions, and are inverses if the following is true. I'll make this a little bit larger after I put it in there. So composition of f and g is equal to x, and composition of g and f is equal to x. So that's when you two functions are inverses of each other. For example, if I got f of x is equal to 3x minus 1, and g of x is equal to x plus 1 over 3. And the question is whether they're inverses of each other. Well, I had to find a composition, go in both directions. So we'll first find a composition of f and g, which is f of g. And we're going to take our f of x, which is 3x minus 1, and we'll replace the x with parentheses. So we got 3 times parentheses minus 1. Now remember, whatever's inside of parentheses here is automatically what we're going to put in here. So put g in there. But g is equal to x plus 1 over 3. 3's would cancel. We got x plus 1 minus 1. The 1's would cancel. We'd have x. Now that's the first part. Composition of f and g is equal to x. We also have to find the composition going the other way. So we got the composition of g and f, which is g of f. So I'm going to take my g of x, which is x plus 1 over 3, and replace my x with parentheses. Now whatever's inside the parentheses here automatically goes in here, so we'll put f in there. So then we got 3x minus 1. The minus 1 plus 1 cancels, and we got 3x over 3, and the 3's cancel, and we get x. Now since both of those give us x, then the answer is yes, these are inverses of each other. Now if one of them could not be simplified to x, you get like 5 or 7, or 3 plus x, or something other than a single x, then they're not inverses. Now next topic is to find the inverse. So let's take a look at that. So finding the inverse of a function. Step 1, replace f of x with y. This is assuming you can find the inverse. If f of x is not 1-to-1, you shouldn't even be trying to find the inverse. Step 2, interchange x and y. Step 3, solve for y. Step 4, replace y with your inverse notation. And step 5, if necessary, use the graph to figure out how to make the inverse 1-to-1. So for example, if I had f of x is equal to 1/3 x minus 2, and I'm asked to find the inverse. Now step 1, replace f of x with y. So we got y is equal to 1/3 x minus 2. Step 2, interchange x and y. So we got x is equal to 1/3 y minus 2. Step 3 is solve for y. So I'm going to multiply everything by 3. So I got 3 times x, 3 times 1/3 y, minus 3 times 2. So that gives us 3x, those 3's cancel, got y, minus 3 times 2 is 6. Take negative 6 over, it becomes a positive 6. And then step 4, replace y with your inverse notation. So the inverse of f is equal to 3x plus 6. Now this is 1-to-1. When I say it's 1-to-1, you look at that list I gave you, where you can't have an even power, you can't have an absolute value, you can't have a plus or minus symbol. This doesn't have any of those, so this is fine. And that's our answer. We'll clear that off. And let's take a look at section 4.2, exponential functions. Now step 1, we want to graph exponential functions. Let's say we had f of x is equal to 3 to the x minus 1 plus 2. Now this is an exponential function. If you're wondering what identifies an exponential function. If you got a variable in the exponent, that's an exponential function. Now the trick to graphing these is to make sure that you put parentheses around the exponent, assuming you have more than a single x or single number there. Other than that, we probably will type in as you see it. So let me get to that point. A little slow coming up. There it goes. So press our y equals, press our clear, and we got 3 caret, and I'll do my beginning parentheses, x minus 1, close parentheses. Now you have to make sure you do a right arrow key to get out of the exponent if you go on the newer TI-4s. I don't have one of the newer ones here, so I don't have to do the right arrow key. And then plus 2, and then graph. And that would be our answer. And you'll notice a pattern, because this same pattern repeats for every one of these problems. It's grown slow, and then it flies out of sight. Now let's take a look at an exponential function dealing with e. We got f of x equal to e to the x minus 4 plus 1. So I go to my y equals, clear. To get e, I do second ln. It puts e caret beginning parentheses, x minus 4, closing parentheses, plus 1. And then graph. Now again, it's grown slow, and then flies out of sight. That's just the nature of exponential growth. Now evaluating an exponential function base e, if I had, for example, I was trying to think of an example, e to the 5th, I think that's what they're asking for there. To evaluate that, e is just a number. It's 2.7, a bunch of decimal places, kind of like pi. So we're going to take e to the 5th power. So I exit out, do second mode, E, you do by second ln again. This is natural log actually. And then we put 5 in and then press enter. And that gives us our answer. Now this says use exponential functions to compute compound interest. We got two formulas dealing with that. So let's take a look at those. Compound interest formulas. If it does not say, let me start with that one, does not say continuous, then you use A is equal to P times 1 plus R over N to the NT power. Now if it does say continuous, then you're going to use A is equal to PE to the RT power. Now A is your ending amount, P is your beginning amount, or your principal. R is your rate, and that's always in decimal form, so if it says 3%, you put in 0.03. And our T is our time, and this is in years. N is the number of times compounded per year. Compounded is a fancy business term for calculated. It's more than that though. They calculate the interest and then they take that interest and put it back into the account, so it compounds, it builds. Now in most of those problems they just give you some values. For example, they may tell you it compounds monthly. And maybe they tell you the P is equal to 1,000, put $1,000 into the account. Our R is 2%, and we leave it in there for 5 years. Well, since it doesn't say the word continuous in this, we're going to use our A is equal to P times 1 plus R over N to the NT power. P is 1,000, 1 plus R, which is 0.02, divided by N, compounded monthly, that means N is 12. Raise the NT power. So we've got 12 times 5. Usually it's best to do a little bit of math before you plug this in your calculator. Specifically, I'm talking about with the exponent. 12 times 5 is 60. Okay, so I'm going to do a y equals. Actually, forget that. I'm not in the y equals. Do a clear in 1,000. Beginning parentheses. I'm pretty well just type in as you see it. 1 plus 0.02 divided by 12. Closing parentheses. Caret 60. And that means at the end of that time I'm going to have 1,105 and 8 cents, rounded 2 decimal places. Now the other formula is a little bit easier. If it says compounded continuously, and let's say P is equal to 1,000, R is 2% again, and time is 5 years. Since it says continuously, we're going to use our PERT formula. A is equal to P e to the RT. Well, A is 1,000, E, R is 0.02, times T, which is 5. So if I go to my calculator, I'll clear that off. We got 1,000 E. So we do second ln, and then 0.02 times 5. You want to make sure when you plug this one in, you do not put any extra parentheses in there. So we got 1105.17. And that's how to compound, compute compound interest. And that's kind of applications too. So let's go down to section 4.3, log functions. Grab a drink here. Now we have our different forms. We have a log form, which is log base b of q is equal to p. And we have our exponential form, which is the form b to the p is equal to q. Now this first topic, convert between log and exponential forms. Let's talk about that. Let's say I have this problem, and we want to put that into exponential form. Well, we first have to identify all of our variables. Now what the b represents, that's got a name, it's called the base. It represents usually a number that follows your log that's smaller than set down. So in this problem, our b would be 3. Then q is what follows that. So whatever's right here is b or q, and then the other side of the equals is your p. Now after you got those identified, then you're going to plug them into your form here. B to the p is equal q. B we said was 3, p is 5, and q is x minus 2. And that's our answer. Now on the other hand, you may have something in exponential form, and you want to rewrite in log form. Well, if it's in this form, or exponential form, then you want to identify your b, p, and q. P is your power, your exponent, so the 2 will be your p. What's immediately to the left of that is your b, your base, and the other side of the equals is your q. So then our log form is log base b of q is equal to p, and we'll plug in everything we identified. B is 4, q is x, and p is 2. And that would be our answer. Now we have some special bases that says if you have, for example, just a log and there's no number there, there's no base, then by default your base is 10. That's a common log. If you have a natural log, it says ln, your base is e. So you may have examples dealing with that, where you got, for example, natural log of 7x is equal to 2, and it says to write it in exponential form. Well, this is in log form. Even though it says ln, that's the same as log. It's just a different base. Don't ask me why they decided to write this base differently, or this log differently. Now we said if we have an ln, our base is e. So since there's no number here, our base is e. Then what's to the immediate left of that, or right of that, is our q. So this is q. And the other side of the equals is our p. So our exponential form is b to the p is equal to q. B is e, p is 2, and q is 7x. And that's our answer. Okay, let me clear that off. Now to evaluate log expressions. Let's take a look at that. If we're trying to evaluate log base 2 of 8. I'm first going to work an example, then I'm going to write down a property. Fairly straightforward idea, but sometimes it's not so easy to get in the right form. Our base is 2, so what we're going to try to do is rewrite this 8 as 2 to the power. And that'd be 2 to the third. Now if those 2's match, then the log and those 2's going to cancel, and the 3 drops out of the exponent, and that's our answer. Now the property for that says we got log base b of b to the p is equal to p. Now throughout this entire chapter, maybe from the second section on I should say, is if you ever have a radical, you want to get it out of radical form. And that's true with all the material we've seen up to now too. So it's, anytime you deal with logs, if you have a radical, you want to get rid of the radical. So this becomes log base 4 of 4 to the 1/2 power. Why to the 1/2 power? Whatever number's in the slot right here is called your index, and by default that's 2. Whatever the number's here is your power. If you do not have one, there's 1 by default. So whatever your number is right here, your power, goes up to your numerator. Whatever number's in the slot goes to your denominator. Now I notice that the 4's matched, so log and the 4 is going to cancel, and our answer is 1/2. Now another property, I'm going to first work an example and then I'll talk about what our answer is. We got 3 to the power of log base 3 of x minus 2. Notice what's matching now, the 3's match. If those numbers match right there, you can cancel those numbers on log, and what follows your log drops out of the exponent, and that's your answer. So our answer is x minus 2. And actually that's these first 2 here. Now graphing a log function. Let's take a look at that. Got y is equal to log x plus 3. Now notice that there's no number here, so the base is by default 10. That's one of our special bases, which works out well because we have a base 10 button. So if we go to y equals clear, this where it says to the left of the 7 says log, that's base 10. So if I push that, puts log on there, and then I want x plus 3. And then I'll push graph. This is almost our answer. Most of these will give you the incorrect graph. Our graph actually looks like this right here. Although that should be a little bit of a smoother curve there. These graphs never just stop. So this appears like it stops right here, keeps going down forever. So that's fine. We got a log button. Now if I'm trying to graph this one, y is equal to natural log of x plus 1. If I go to y equals clear, I got an ln button, so that works out well. X plus 1. and then graph. So again, these graphs are never correct. It actually keeps going down like that. Okay, very nice if you have a log button or ln button. But if you have a different base, we have log y is equal to log base 3 of x plus 1. Now I cover it here, but this is actually right down here. Apply the change of base formula. So we're going to rewrite this using change of base as log of x plus 1 over log 3. Pretty straightforward how it works. Whatever follows your log goes up on top. Whatever your base is goes down below. What's the benefit of this? Well, we have a log button on our calculator. We don't have a log base 3 button, but we do have a log button. So I'll come over here, do my y equals clear, log x plus 1, closing parentheses, divided by log 3, and then closing parentheses, and then graph. And our graph would look like that right there. Grab a drink here. You might look at that and say, well, that's the same as the x plus 1 up there. The y equals ln x plus 1. That's close. Depending upon what your base is, it changes what it looks like. Okay, next section. Section 4.4, properties of logs. It says apply the product, quotient, and power properties of logarithms. And actually they use those. Those are the next two items, so they go hand in hand. So our log properties. Our first one says we got log of something plus log of something. Addition becomes multiplication. You got log of something minus log of something. Subtraction becomes division. If you got a number in front of your log, although it doesn't have to be a number, then you can put that as your power. First one's called your product property. Deals with the product. Second one is your quotient property. Deals with the quotient. And last one's your power property. Deals with the power, if you're in the names. Now we're going to use these. We're going to apply them to write a log expression in expanded form. So let's see what in the world that's referring to. Let me clear this off. Let's say I got y is equal to natural log of x squared y to the third over z to the fifth. This is a single log at this point. We want to split them into multiple or several logs, and would like to get to the point where we have a single variable with a log in front of it. That's our goal. Now you always have to ask yourself, what's the main thing happening in these problems? Here the main thing that's happening is division. When I say main thing, I'm talking about what would use everything in your problem besides the log. So top part divided by the bottom part. Well, division we rewrite as subtraction. So we've got natural log of x squared y to the third minus natural log of z to the fifth. Now in our first log here we have multiplication, x squared times y to the third. And multiplication becomes addition from our first property. So we've got natural log of x squared plus natural log of y to the third minus natural log of z to the fifth. And then our last item we need to do is we need to take those powers and put them out in front. As I said, we'd like to get a single variable with a log in front of it. So this becomes 2 natural log of x plus 3 natural log of y minus 5 natural log of z. And that would be our answer. Now sometimes you may have to rewrite something that's in radical form out of radical form. It's like on this one, we would have, helps to have a log in front of it. There you go, natural log. So we'd rewrite this as x over y to the 1/2 power. Now again, you have to ask yourself the main thing that's happening. And the main thing that's happening here is we got something to a power. So from our third property, we can take the power and put it out in front of our log. Now here on out, the 1/2 has to be out in front of each log as we rewrite it. Now here we got log of something divided by something. So division. Division becomes subtraction. We got y is equal to 1/2 natural log of x minus 1/2 natural log of y. You will not always be able to get the variable by itself. Sometimes you end up with like a natural log of x plus 3. But you get it as close as you can by itself. Occasionally on some of these problems, you'll be able to simplify. Like if you're working a problem down and you end up with log of base 2 of 8 or something. If you have a number you can use the earlier property on, then do so. For example, 8 is 2 to the third. And remember, if these numbers match, the log and those numbers cancel, and we get 3. Drops out of the exponent. Okay, now that was writing in expanded form. Now let's take a look at write a log expression as a single log. So we're going the other direction. So let me clear this off. And grab a drink. So we've got y is equal to 5 natural log x plus 3 minus 7 natural log of x. Now our goal is to merge this into a single log where you just have a log of something. No numbers in front of it, just log of something. Well, we can't use properties 1 and 2 if you have any numbers in front of your logs. So if you ever have any numbers in front of your logs, first thing you do is put as your power. That's natural log of x plus 3 to the 5th power minus natural log of x to the 7th. Now we got log of something minus log of something. Subtraction becomes division. So we've got natural log of x plus 3 to the 5th over x to the 7th. And notice we have a single log now. I shouldn't have had the y equals. I'm thinking of something else. That's where we're actually doing something further with it. As if you're going on calculus or some class like that. Okay, if I have 1/2 natural log of x minus 5 natural log of y, and want to merge this into a single log. Well, the order of operations says we do what's inside of parentheses first. So a natural log of x I can't do anything with, but the 5 I can put as my power. So I got 1/2 natural log of x minus natural log of y to the 5th. Now we got log of something minus log of something. Subtraction becomes division. So we got x over y to the 5th. And we have a number in front of our log. And you can put that number as your power. So we're going to have natural log of x over y to the 5th to the 1/2 power. And again, we got a single log there, log of something. We already looked at change of base. Now exponential and logarithmic functions. First thing we're going to take a look at is solving log equations. And this will be the equality of exponents. And that says if you got b to the p power is equal to b to the q power, then you set p is equal to q. Fairly simple idea. Sometimes not so simple to get in the right form. Let me clear this off. For example, if we have 2 to the x is equal to 8, the equality of exponents, what we do is we start with our larger number, typically, and we try to rewrite it as the other number to a power. Well, 8 I can rewrite as 2 to the third. Equality of exponents says if these are both 2 to a power, I can cancel the 2's and set the exponents equal to each other. And when I do that, then my problem's already solved. Like I say, though, not always so easy to put it in the right form. Let's say I got this problem here. Well, first off, I said earlier we don't want any radicals anywhere in this chapter, so I'm going to rewrite that as 2 to the 1/2. Now once I do that, I see it's really close to being in the right form. I just need to move this 2 to the 1/2 up on top. So then we'll have 2 to the x plus 3 is equal to 2 to the negative 1/2. Remember, when you move anything opposite where it's at in a fraction, the sign of the exponent changes. Now they're both 2 to a power, so I set the exponents equal to each other. So I got x plus 3 is equal to negative 1/2. It's like the 2's cancel. Take 3 over, we got negative 1/2 minus 3, which gives us negative 7/2. Now sometimes you have to focus on both sides. For example, 16 to the x plus 1 is equal to 8 to the x minus 2. Well, if I start with my larger number, the 16, there's no way I can rewrite it as 8 to a power. So what we do is we'll look at both sides. And I see I can rewrite 16 as 2 to the 4th. And I can rewrite 8 as 2 to the 3rd. Now notice that these already have an exponent. So when we put our new exponent up there, we put multiplication in between. Well, now they're both 2 to a power, so those 2's going to cancel. And I set the exponents equal to each other. So that gives us 4x plus 4 is equal to 3x minus 6. Get everything with an x on one side, so I take 3x over, take the 4 over. 4x minus 3x is 1x or x. Negative 6, negative 4 is negative 10. And that'd be your answer. Let's take a look at one that doesn't work. So for example, if I have 3 to the x is equal to 5. There's no way I can rewrite the 5 as 3 to a power. There's no way I can focus on both sides. So we have a general technique for solving exponential equations. First step, get the part with the variable and the exponent by itself on one side. Step 2, take a natural log of both sides, ln. Step 3, use properties of logs to get the variable out of the exponent. Step 4, solve for x, or whatever variable you're dealing with. Okay. Step 1, get the part of the variable and exponent by itself on one side. What I mean by that is we just had 3 to the x power. We don't have nothing in front of it, nothing after it. Well, it's done. Step 2, take ln of both sides. So we've got natural log of 3 to the x is equal to natural log of 5. Step 3, use properties logs to get the variable out of the exponent. So we'll take the x and put it out in front. So we've got x natural log of 3 is equal to natural log of 5. Step 4, solve for x. So we're going to divide both sides by ln of 3. Those natural log of 3's cancel, and we got x is equal to natural log of 5 over natural log of 3. And you can plug that in your calculator to get the decimal approximation. That's the exact value right there. Now consider if I had a different example. This right here. Actually, let me work one where I have to get something. There we go. It's not by itself. So step 1, get the part of the variable and the exponent by itself on one side. So here I'm going to take the negative 1 over. And we got e to the 3x minus 1 is equal to 4 plus 1. 4 plus 1 is 5. Step 2, take natural log of both sides. So we got natural log of e to the 3x minus 1 is equal to natural log of 5. Now step 3, use properties of logs to get the variable out of the exponent. Natural log and e cancel each other. So that gives you 3x minus 1 is equal to natural log of 5. Step 4, solve for x. I'll take negative 1 over, becomes a positive 1. And divide both sides by 3. So we got 1 plus natural log of 5 over 3. And that'd be our answer. Now let's take a look at log equations. Example of a log equation. If you have log base 3 of x minus 1 equals 2. This is what a log equation looks like. Now solving log equations. First step, get everything with a log on one side, numbers on the other side. Step 2, use properties of logs or basic algebra to get a single log. Step 3, use the definition of a log to rewrite in exponent form. This is the b to the p is equal to q definition. Step 4, solve for x. Step 5, semi-check your answers. You don't have to fully check them, but you have to semi-check them. Now I'll talk more about what that means. For this example here, our first tip is to get everything with a log on one side, numbers on the other side. Now that's what we have. Step 2 says get a single log. We have a single log. When all is said and done, you should just have it saying log of something. Nothing in front of it, nothing after it, just log of something. Step 3, use definition log to rewrite in exponent form. Remember the number that follows your log here is our b, and what follows that is our q, and the other side is our p. Our exponential form is b to the p is equal to q. So we plug in what we identified. B is 3, P is 2 and Q is x minus 1. And then step 4 is solve. Well, 3 squared is 9 equals x minus 1. Take negative 1 over, becomes a positive 1. And we get x is equal to 10. Maybe. If we plug that back up here, 10 minus 1 is 9. We just have to make sure that we didn't create a log of a 0 or log of a negative number. Well, 9 is not 0 and it's not negative, so we're fine. Now I'm not going to finish these problems, but I'm going to show you the setup. Mainly because I wouldn't be able to make these up, so they actually worked out nice. Okay, step 1. Get everything with a log on one side, numbers on the other side. Well, everything with logs over here, numbers over here. Step 2. Use properties of logs to get a single log. Well, we've got log of something plus log of something. Addition becomes multiplication, so this becomes log base 2 of x minus 1 times x plus 1 equals 7. Or log base 2 of x squared minus 1 equals 7. Step 3, use definition of log to rewrite an exponent form. Remember, this is our b, whatever number is right here. This is our q, and the other side of the equals our p. So our exponential form is b to the p is equal q. b is 2 to the 7th power is equal to x squared minus 1. And then you work it down from there. Now if you had a different problem, say you had log of 3x minus 1 minus log of 2x plus 3 is equal to 1. Well, we'd want to merge these into a single log, and subtraction becomes division. So this is log of 3x minus 1 over 2x plus 3 is equal to 1. Now our base will be whatever number's here, and since it just says log and there's no number, it's by default 10. Remember, if it's ln, it's base e. This will be our q, and this will be our p. So our exponential form is b to the p is equal to q. Well, b was 10, p is 1, and q is 3x minus 1 over 2x plus 3. And then you solve it from there. Now there's some other applications here. I'm not going to go over those. I got quite a bit of YouTube videos on how to solve different applications, so you can watch those. I'm going to go ahead and stop the recording, and I'll see what questions you have.